Hello everyone, nice to talk to you all. So this class we're going to continue our topics on the fundamentals of environmental engineering and science. So specifically we're going to talk about sulfur dioxide and nitrogen dioxide. So both of these are gaseous air pollutants, right? So before we introduce the new contents, let's again do a quick recap. So in our last class, we talked about the particulate matter, right? So we know that PM is one type of the criteria air pollutant, which means that it's very important, right? Both because of its toxicity and also the large amount that's being emitted. So it can have a huge impact on our daily life, right? So it can impact the human health, climate change, material. It can also be used as materials, so on. So in terms of the sources of the PM, they can be generated both from top-down method and bottom-up method. So what that means is these PM can be generated by disassembling or fragmenting larger pieces of objects, but also they can be formed from molecules, right? Like the combustion, and then you form those carbon species, and then they will further collide and then form larger particles. So in terms of the removal, we quickly went through three different types of removal devices, right? We talked about the cyclone, which is using the circular or rotational movement of the particles, because in order to keep them rotating, we need to give them an external centrifugal force, but we don't have that in the system. So that's why the larger particles will get spinned out. It's just like a washing machine, right? And then they will just further fall down and then get collected. And for the electrostatic precipitator, that's using the electrostatic force that's acting onto the particles. So we first charge these PM and then let them go through electrostatic field and then remove these particles. So in terms of the backhouse filter, we basically just create a filter that stops these particles from penetrating through, right? And also the filter has the highest efficiency in removing the particles. So at the last, we introduce how the particulate matter or how our knowledge might be related with the current COVID-19 situation. So in this class, we're going to talk about the sulfur dioxide and nitrogen dioxide. We know that both of them are criteria air pollutants, right? So they're emitted in large quantity, but also they're toxic to our respiratory system. And also they have the ability to form the acid rain, right? So before we further introduce the source or the control technology of the sulfur dioxide or nitrogen dioxide, we need to basically continue our discussion on the unit conversion. So in the class before the particulate matter, at the last, we introduced that we basically went through this table here. So you can see that it's labeling the concentration or the limit that's required by the NAAQS. Basically, this is the air quality standard, right? So it limits the concentration here. So you can see that there are a lot of units. You can have the ppm, right? So ppm means parts per million. So 1 ppm simply means that among a million of the air molecules, there's one molecule of the carbon monoxide, for example, here. So 9 ppm just means that among 1 million of the air molecules, there are 9 molecules of the carbon monoxide. So following that, we also have a bracket, which is showing a mass concentration, right? So this is the mass of carbon monoxide per cubic meter of the air here. So basically, my question is, are these two the same, right? They have to be the same. Otherwise, it's meaningless to give two numbers here, because the factor will just follow the value that has a higher number here, right? The higher actual number here. So then we have a question. So how do we convert these units? Right? We'll talk about the unit conversion. So basically what we're trying to do is we want to convert these three types of units. So the first type is the absolute concentration. So absolute concentration just means how many numbers or how many moles are there per unit volume of the air. So for example, we can have the unit of mole per liter, mole per cubic meter, right? Number per liter. So number just means how many numbers of molecules. For example, if we know how many moles are there, we just need to multiply the NA, which is an Avogadro number. And the Avogadro number is 6.02 multiplied by 10 to the 23, right, per mole, right? So we can also use number per cubic meter, so on and so forth. So we can also show these gas molecule concentration in mole fractions or number fractions. So this is just using the unit of ppm or ppb. So these are basically the number of the gas pollutants over the number of air molecules, right? So we can either use percentage, right? ppm, parts per million, parts per billion, parts per trillion, so on and so forth. So how do they convert from each other? So 1% simply means that's 0.01, right? 1 ppm, that's going to be 0.000001, right? And similarly, ppb is going to be further 30 here and then 1 here. Okay? So similarly, we can further calculate ppt here. So basically, the mole fraction or number fraction is just the number of the gas molecules that we're interested in over the total number of the air molecules. So finally, we have this mass concentration. The mass concentration is just the mass of this specific gas over the volume of the air ensemble here, right? So basically, we have the question of how do we convert from one to each other. For example, here, we're converting, for the carbon monoxide, we're trying to convert from a mole or number fraction into mass concentration. So how do we do that? So everything will start with the ideal gas law. So I'm actually labeling some of these processes here. So maybe it will be better that we just go through this process again. So we can use that as a reference and we'll derive the equations here again, okay? So basically, for any gas ensemble or air ensemble, we know that there's an equation that's governing the properties of the gas, which is ideal gas law, right? So we're also introduced in our first or second class. So ideal gas law simply means that for all of these gas molecules, right, in a like an imaginary boundary here, in a certain volume here. So the pressure, volume, temperature, and number of gas molecules will follow a law, right? It will follow a relationship, which is PV equal to nRT, right? So people also call them Pavnert for better memorizing the equation, right? So here we have to also notice the units for all of these terms. So P here will have a unit of Pascal, right? V has a unit of meter cube. N has a unit of mole, right? R has a unit of joule per mole per K. And T has a unit of K, okay? So basically, if we calculate the unit on left-hand side and right-hand side, we see that on the right-hand side, the unit will be joule because everything got cancelled, right? Mole and K got cancelled. On the left-hand side, we know that Pascal multiplied by meter square, that's going to be the force, which is Newton, right? Right, so we're adding 1 Pascal on a unit surface area, right? That's going to give you Newton. And Newton multiplied by meter, that's going to be joule. So in this way, the units are conserved, right? So this is the ideal gas law. But actually, for each species, or each gas species inside, for example, originally we were talking about the air as a total ensemble. Right now, we are seeing some air molecules. We assume that there are some carbon monoxide molecules in this air. So the ideal gas law also work for carbon monoxide. So the equation will be a little bit different, but they still follow the same pattern, which is PA multiplied by V equal to NA multiplied by RT. So here, the PA is just the partial pressure of species A. And the Na here is the moles of the species A, right? So this A can apply for any gas species, for example, carbon monoxide, nitrogen dioxide, so on and so forth, as long as it's a gas species. But particulate matter won't work, right? Particulate matter is not a gas species. Actually, it's a cluster of molecules. So the ideal gas law won't work for particulate matter, and it won't work for lead either, right? So now we have these two important tools, right? Two important equations. Now we can try to convert the different units here. So basically we have PV equal to nRT and PAV equal to NART, right? So now let's look at what is absolute concentration. Absolute concentration is just means how many moles of A there in this gas ensemble. So if we use the parameters shown in here, so the absolute concentration is just Na divided by V, right? So the absolute concentration for carbon monoxide is just the number of moles of carbon monoxide over the entire volume, right? And similarly for the mole fractions, the mole fraction is just the number of the gas molecule we're interested in divided by the number of all the gas molecules, right? That's Na divided by N. And finally, for the mass concentration, this is just going to be Ma divided by V, right? So the gas or the mass, for example, mass concentration of carbon monoxide in the air is just the mass concentration, the mass of the carbon monoxide divided by the total air molecule. So basically, we have these three parameters. So the unit conversion is just trying to convert these three from one another. So how do we do that? So if you notice here, actually I'm already listing the steps we do the calculation, right? So if we start from this the absolute concentration, which is Na divided by V. Okay, so it is quite easy to convert this thing, the first one, into the third one, because the number of moles of A is just calculated by the mass of A. Let me write it down here. It's just calculated by mass of A divided by the molecular weight of A, right? So we can easily plug this term in, and then we can calculate this relationship here. So basically, the absolute concentration is just the mass concentration divided by the molecular weight of A, right? So this is how we can convert from 1 to 3, right? And furthermore, what we need to do is basically to further convert this whole term into the mole fraction here. So an easy way to do that is basically to put out a whole equation of the V, right? So based on the PV equal to nRT, we know that V, or the volume, is equal to nRT divided by P, right? Therefore, the Na divided by V, right? Let me write it out. Na divided by V, if we plug in this equation here, then it's just going to be Na divided by nRT multiplied by P, okay? And then we can have Na divided by N multiplied by P divided by RT, right? So now this is how we can convert this absolute concentration into the mole or number fraction, right? So this is how we can do that. So basically we have this equation here, okay? So now we can convert from mass concentration, we can convert these two, right? Mass concentration into mole fraction. And since we have these two equations here, we can easily convert from mole fraction to absolute concentration. We just need to do some rearrangement. So basically, if we further want to calculate from the mole fraction into the mass concentration, we can just do a rearrangement. Let's say we're trying to look at these two terms here, or trying to look at these two relationships here. Then we can just rearrange by multiplying the molecular weight of A on both sides, right? Both sides. So MA divided by V is just going to be the mole fraction or mass fraction, or the number fraction, multiplied by P multiplied by molecular weight of A divided by RT, right? So I know that this is a little bit complex here, but you can see how we can convert these three different units from one another. And this is actually quite important when we're trying to look at the concentration of the air pollutants. This is how we basically make sure that the air quality is good enough, satisfies the requirement, right? So the instrument that we use normally will just give us one type of unit. And we can use this equation to convert from one another, right? So for the equation derivation, you might feel that it's a little bit complex. But let's do some quick examples here. Actually, one quick example to see how we can use this equation, right? So here, I have three problems. Let's just look at the first one, and the other two will be your homework problems. So this problem wants to convert 1100 milligram per cubic meter of carbon dioxide into the units of ppm. So just by looking at these units, what we're trying to do, what are we trying to do here? So the unit here is milligram per meter cube, which means that this is mass concentration, right? And ppm is the mole or number fraction, right? So if we go back here, we're converting from this one to this one here, right? So basically, we're converting from MA divided by V into NA divided by N. So how do we do that? We have this equation here, right? So MA, we know that MA divided by V is equal to NA divided by N multiplied by P multiplied by molecular weight of A divided by RT. So this is what this equation is telling us, right? So we have the mass concentration of carbon dioxide ready. We have the pressure, right? The pressure here is 1 atm, right? Temperature is 25 Celsius. The R here, the gas constant, I hope everyone know that, it's 8.314 joule per mole per K, right? The molecular weight of A, or carbon monoxide, we know that it's 44 gram per mole. So basically we have everything. We can just calculate this Na divided by N here, right? So now how do we do that? Again, I'm showing this procedure here, but I think that it's better that we go through this calculation all together, right? So we're trying to calculate Na divided by N, which is in the mole or number fraction, right? So because of that, Na divided by N is going to be equal to Ma divided by V multiplied by RT divided by P multiplied by molecular weight of A. So we're rearranging this equation so that this term comes to the left. Okay? So now let's start to plug in all the numbers. So the mass concentration of the carbon dioxide is 1100, but that's milligram per meter cube. We know that to calculate all of these equations, we need to make sure that all of them uses the standard unit, right? So in terms of the mass, the standard unit is kilogram. So we have to first convert the milligram into kilogram. So that's going to be 10 to the minus 3. We convert that into gram. And then multiply another 10 to the minus 3 to convert it into kilogram. So that's going to be kilogram per meter cube, right? And then the R will be 8.314 joule per mole per K, okay? So the T is 25 Celsius. We cannot directly plug in 25, right? Because that has to be in the unit of Kelvin. So that's why the temperature is actually 25 Celsius, which is equal to 273.15 K plus 25 K, which is 298.15 K, right? Here we'll just plug in 298.15 Kelvin, and then we'll divide that by the pressure. So what is the standard unit for pressure? That's going to be Pascal, right? 1.01 multiplied by 10 to the 5th Pascal, and then multiplied by the molecular weight of A, or the molecular weight of the carbon dioxide, right? We know that the carbon dioxide has a molecular weight of 44 grams per mole, but again, we want to convert it into standard units, which is 44 multiplied by 10 to the minus 3 kilogram per mole. You can see that this is a pretty long equation, and also you can play with the units here, and you can see that the units actually will conserve and will change to 1. So as a matter of fact, since we have enough time, we can just do a demonstration here, because you can see that on the left hand side, this is just mass, or this is just a mole or a number fraction. So if that's a fraction, then the unit should be 1, right? Now let's look at the right hand side. So on the right hand side, let's see what's going to happen. So basically the units, let's write everything out, okay? So that's going to be kilogram per meter cube, right? And then joule, mole, K, right? And we have K on the top. And further, we have Pascal on the below, right? We're trying to copy everything, right? This thing will convert to here. This K here is here, and then Pascal. And then we have mole to the top, and then kilogram at the bottom. So we're converting this thing into here. Okay, so now let's try to cancel. Let's see if everything can cancel and give us a unit of 1. So the mole and mole will cancel out, right? Let's just pick the easy things here. Kilogram and kilogram will cancel out. So now we just have joule divided by Pascal multiplied by meter cube. Again, Pascal multiplied by meter square, that's Newton, right? And 1 Newton multiplied by 1 meter, that's going to give you joule, right? So this thing will cancel out too. So we're going to have a unitless term here. So now if you use a calculator to plug in everything, so we have to make sure that everything uses a standard unit, okay? Otherwise, you will not be able to get the correct answer. Okay, so if you use a calculator and then plug in everything, you can find out that the number is 0.000613. Okay, so it wants us to use ppm. So ppm is parts per million, right? So what we do is we can directly multiply by 10 to the 6, which is 1 million, and that's gonna be 613 ppm. Okay, so this is how we can convert 1 unit to the other. So here, it's also giving you 2 another problems here. The second one is quite similar to the first one, except that we're using micrograms, which is further lower. It wants you to convert that into ppb. And the third one is actually the reverse. It wants us to convert the mole fraction back into mass concentration. So since we have this equation here, so we can directly plug in the ppb here, right? So that's the number fraction, or the mole fraction, and then we can plug in the parameters for the sulfur dioxide, right? So I hope that this is clear enough, and you can do some more practice from your homework. Okay, so now let's get into the topic on the sulfur dioxide and nitrogen dioxide, which is the main topic for this class. So we know that the sulfur dioxide and nitrogen dioxide, they are harmful because they can penetrate through our respiratory system, but also they're categorized as air pollutant because they have the ability to form acid rain and further damage the property, right? So this is showing a picture of the very famous construction in India. So this is called the Taj Mahal, right? So this construction is made of limestone, right? And then because of the it's because of the air pollution, right? Generating these sulfur dioxide and nitrogen dioxide into the air, they can further react with water and then form sulfuric acid or nitric acid. Okay, so we know that limestone is made of calcium carbonate, and actually we talked a lot about the calcium carbonate in our water treatment because they can neutralize the acids, right? So because of that, once you form the acid rain and then falls onto the construction, it's gonna corrode the surface. So actually India is costing a lot of money every year to remove these corrosions here because that's gonna make this construction look yellowish, right? So this is how you can see the sulfur dioxide, nitrogen dioxide might damage our properties here. So it not only affects the construction, it also harm the plants. So this is again showing a picture of the Smoky Mountain. So I really like this place, so that's why I'm using that for a lot of examples. So in the Great Smoky Mountain, especially when you go further higher altitude, where the trees are becoming needle trees, right? So those are typically the plants or the trees that can endure lower temperature. So those trees are also very sensitive to acidic species. So whenever you have acid rain, once they fall onto these trees, and then they're going to cause diseases to these trees. So that's why you can see areas that has previously been very beautiful forests or the pine trees, right? And then they got damaged by these acid rain here. So this plot, you might be already quite familiar with it. So this is a cleaner version of the basically the trend of the sulfur dioxide emission since 1970, right? So this trend is actually coming up to 2017. So you can see that ever since the establishment of the EPA, the concentrations or the emission of the sulfur dioxide reduced very significantly. Actually, you can see that right now it's probably around 3,000, right? 3,000, basically it's 3 million tons. But look at where we were maybe 50 years ago, right? So right now the emission rate is just 1/10 of the previous condition, which is really showing that people are raising the awareness of our environment protection, right? So we have to generate profit for running all of these businesses or running all of these industries, but at the same time, we should reduce the pollution that we're posing onto the environment. And we can see that this is not harming the economy, right? Actually, it's promoting the economy because it's giving more jobs, right? So in this way, we can live more sustainable, right? So this is basically the idea of why we should set up the EPA and then follow all of these environmental policies, because they not only protect our environment, they can also generate more jobs, and also they can promote the new technologies, right? People always try to use those or deploy those less expensive or highly advanced technologies, okay? So as we can see, the sulfur dioxide actually reduced quite significantly. So what control technology did we use? So in terms of sulfur dioxide, there are two major control methods. So the first one is that, so basically the sulfur dioxide is emitted, almost all of them are coming from fossil fuel combustion. Okay, so almost 100%, and the same for nitrogen dioxide. So this is basically the fossil fuel combustion is the only way that we can generate sulfur dioxide or nitrogen dioxide, okay? So more specifically for the sulfur dioxide, the control technology can be divided into two methods. So first is before combustion, so which is before the fossil fuel combustion, and the other method is after the fossil fuel combustion. So in terms of the carbon dioxide, or which is we're not going to cover later. So so basically for the carbon dioxide, we can also have a third technology, which is in combustion. So basically you can see that we can apply these control techniques in all different stages of combustion, right? So in terms of the sulfur dioxide, we're just going to use these before and after combustion. So for before combustion technology, that is called the fuel desulfurization, and that's widely used in oil refineries. So basically, a major product from the oil refinery is the gas, right? The gasoline. So we're converting the crude oil into gasoline and also other species. So during the refinery process, one major goal is to remove the sulfur. So you may wonder, why can't we just leave the sulfur in the gasoline and then let the cars process it? So that's because actually the sulfur has a pretty high percentage in the crude oil. And once it's combined into the gasoline, then it's going to be quite difficult for us to control that, because you think of the parts that's making the cars there. It's typically made of metal, right? So once you form these sulfur dioxide and further form the sulfuric acid, then it's going to be very difficult to control these species. So that's why it's regulated that people have to process or remove these sulfur species before we deliver them into the customers, right? So that's why the oil refinery will use these fuel desulfurization. So before 1970, a major thing they do is actually first convert those sulfur that's bonded with the hydrocarbons. For example, we can have some hydrocarbon that's bonded with the sulfur here. So they can use some techniques to convert this organics into hydrogen sulfide. Okay, so basically you can use the hydrogen, and then what's going to happen is that you can introduce hydrogen here, and then under certain temperature, right? Under high temperature, high pressure, you can generate or convert these sulfur-containing fuels into hydrogen sulfide. And you know what they further do? Because once they extract the sulfur, you can convert or concentrate all of these sulfur-containing species. So basically, before 1970, what the oil refinery does is they directly combust all of these hydrogen sulfide. So you can see that after combustion, you can generate water and sulfur dioxide. So basically, this is not pollution prevention or pollution control. This is just a redistribution of the pollution. So instead of distributing the sulfur dioxide problem into the cars or into the customers, the oil refinery will just generate a huge amount of sulfur dioxide at the plant itself, at the devices in the refinery, right? So this is a redistribution of the air pollutant. It's not solving the problem. So after the establishment of the EPA, people have to think of ways to convert or to collect all of these sulfur dioxide. So the process that they invented is actually very clever. So this process is called the Claus process. And what it does is, since we already have these hydrogen sulfide here, why can't we just combine them with the sulfur dioxide? Right? We can combine them with the sulfur dioxide, and then the hydrogen and oxygen here can form water. And then the other product we can directly get is just the sulfur. So the sulfur solid themselves. So here I'm writing out the equation or reaction for this process, right? So you can generate basically 2 numbers of water and then 3 number of sulfur here. So you can see that this is a very clean process. So not only we're not emitting the sulfur dioxide, but also we're converting them into water and sulfur solid, right? So then you may imagine that, so you may have the question, what can we do with all of these sulfur? So we have a huge demand of sulfur, right? So sulfur can be used as gunpowder, right? So they can be used in armors, right? Artilleries. So they also can be used in our daily lives. For example, they can be used in the fireworks. Okay, so next time when you watch the fireworks, you can think that, oh, some of these are actually from the crude oil. So basically, the production of these sulfur from the oil refinery is so large that it actually covers 90% of the domestic usage of sulfur in the United States. So basically 90% of the sulfur that's on the market in the US are converted from or generated from this Klaus process. So you can see that we're really making a great difference by using this chemistry process here, right? So we're also generating these high-value products. So of course, some of these sulfur generated from the Klaus process are also being exported in other countries and further make profits. Okay, so this is a before combustion or the fuel desulfurization. And in terms of the after combustion or the flue gas desulfurization, this is typically used in the coal-fired power plant. So for the coal-fired power plant, the problem is that the coal are solids there. So it's not like the crude oils, which is in liquid or in gas form, that you can easily apply these sulfur extraction process. So since the coals are small particles or small solids there, so if we apply the same chemical process, then it's not going to be a complete process for extracting all of these sulfur. So we have to deal with the sulfur dioxide after we go through this combustion process. So until now, this is a map showing the all the power plants that already have the flue gas desulfurization or the FGD, or those who haven't applied these methods yet. So you can see that in the United States, not all the coal-fired power plants are using the FGD method, right? So although some of them are planning to do that, but actually you can see that many of them or more of them, right, are not using these FGD methods. So we're still emitting a lot of sulfur dioxide into the atmosphere. So in terms of the FGD process, we can probably go through this short videos here. That is showing the mechanism of removing the sulfur dioxide from the
In some instances, sulfur dioxide from combustion is removed from the flue gases by using it either to produce sulfuric acid or gypsum for construction. These products can then be sold to help offset the cost of running the flue gas desulfurization plant. In both cases, oxygen is used to help encourage the necessary reactions that need to take place. In the case of sulfuric acid, adding excess air to the sulfur dioxide and vanadium oxide converts it to sulfur trioxide, SO3. When combined with water, this produces H2SO4, or sulfuric acid. In the case of gypsum, limestone slurry used in wet scrubbing processes combines with sulfur dioxide to produce calcium sulfite. When subjected to a forced oxidation process involving the addition of water and oxygen, the sulfite is converted into gypsum. In addition to these processes, oxygen is also required in flue gas desulfurization processes using seawater. As the seawater absorbs the sulfur dioxide, oxygen is added, creating a mix of sulfate ions and hydrogen, which in turn converts to water and CO2 gas. In all three cases, using an oxygen probe to accurately measure oxygen concentrations can help to regulate the conversion of sulfur dioxide. For more information about ABB's AZ Analyzer range, contact your local sales representative or visit www.abb.com/. The case of
So basically we can stop here and then look at this process here.
or sulfuric acid.
So this is a process that's this huge cylinder in the middle here is the basically the process that's removing the sulfur dioxide. And we typically call this process, this device, as a scrubber or limestone scrubber. So basically we're introducing the limestone or limestone slurry droplets from the top, and then while they form these droplets falling downwards, they'll absorb the sulfur dioxide that's in the gas species and then form some products. And finally, they'll settle down in this container. And then after we dry them, we can get gypsum. So you can also see this device on the left, which is introducing air into this scrubber here. So actually, this device on the right is a electrostatic precipitator, which we introduced last class for removing particulate matter, right? So you can see that actually there's a sequence of these devices here. So you may imagine, why can't we just remove the sulfur dioxide first and then remove the particles? It is difficult because once we generate those particle containing flue gas, if we first introduce them into the scrubber here, then the droplet will also absorb those particulate matter, right? And also it will basically affect the grade or affect the quality of the product, which is a gypsum in our final product. So that's why we were going to use this particulate matter removal process first to get rid of the particles, because this process will not affect the gas pollutants, and then introduce them into the scrubber to remove the sulfur dioxide. If we reverse this problem, then the ESP probably don't have that much of a significance, because many of the particles are removed from the scrubber process. Okay. So let's go back to the contents here. So basically, people use this scrubber to remove the sulfur dioxide during the coal-fired power plant process. So the limestone is made of calcium carbonate, right? And people can also use lime. And we have introduced these species during the water treatment or the wastewater treatment, right? So they're typically the same, right? So except that their mass is a little bit different. So people can also use the spray drying. So instead of using these droplets, they basically introduce these dry particles into the system and directly achieve everything achieve everything in the gas phase, not in the liquid phase, right? So this is for the sulfur dioxide control. And again, I'm showing the device that's removing the sulfur dioxide, right? So this is flue gas. The flue gas already been cleaned in particulate matter, right? And then we'll introduce the limestone to these nozzles here. So the nozzles are generating these tiny droplets, and as the gas move upward, they're going to remove the sulfur dioxide. And finally, if we further introduce the oxygen inside, we know that calcium sulfide has a low solubility. So at the end, we're going to form the gypsum, and after drying that, we can sell them for profits. So this is also showing the entire coal-fired power plant system. So there's also a video here. You can feel free to check it after the class. So again, I want to emphasize that the particulate matter removal process is before the scrubber, because otherwise it will affect the quality of the product that's coming out of this scrubber here. So in terms of the nitrogen oxides, it's quite similar to the sulfur dioxide, right? Except that the sulfur dioxide is just has one type of like relative species, which is sulfur trioxide, right? But in terms of the nitrogen oxides, it has a whole families of these nitrogen oxide, different types of nitrogen oxides, and typically they can convert from one another. And we need to notice that the nitrogen oxide or nitrogen monoxide is most commonly seen at high temperatures, but at lower temperatures or room temperature, ambient temperature, the nitrogen dioxide is more commonly seen. Okay, so again, the nitrogen oxides are typically generated from coal-fired power plants or the fossil fuel combustion. So here I just want to let you know that basically the temperature will affect a lot of things. So it's raising the temperature from room temperature, which is around 300 Kelvin, to 2200, which is around the combustion temperature. So here is showing the equilibrium constant for this nitrogen and oxide reaction, because whenever we burn the fossil fuel, we also introduce nitrogen and oxygen inside. So these two species will combine to form oxide, nitrogen monoxide. So you can see that the equilibrium constant increase exponentially as we increase the temperature. So basically at 2200 Kelvin, this equilibrium constant is very large here. So what that simply means is that the concentration of the nitrogen monoxide is going to increase, right? So basically under high temperature, we're going to form more nitrogen monoxide, and that means more pollution. So people have also done other studies trying to look at how other parameters might influence the system. So this picture here shows the influence of temperature and residence time again. So basically for each curve here, it represents under certain residence time under high temperature. So residence time just means how long the flue gas stays under in the combustion of the coal-fired power plant, right? So you can see that for each constant residence time, the higher the temperature, the higher the nitrogen monoxide concentration. This is what we saw from here. But you can also see that at a constant temperature here, the longer the flue gas stay, the higher the nitrogen monoxide concentration. So basically, if the temperature increase, NO will increase, right? If the residence time increase, the NO will also increase. So here is further showing how the gas mixture is affecting the NO concentration. The equilibrium, so the x-axis is showing the equivalence ratio. So this simply means what is the ratio between the oxygen and the fossil fuel. Okay, so if they are following the equilibrium or the stoichiometric ratio, then that's going to be 1. So basically, if there is less oxygen, that's going to fall below 1. If it's more oxygen, it's going to be above 1. So you can see that the NO concentration always happens when it's burning under the equilibrium, under the equivalence ratio, right? For example, let's say we're trying to burn methane and oxygen, right? So we know that the stoichiometric ratio is going to be 1/2, right? So this is under the equivalence ratio of 1. So if it's below that, then it simply means that there are less oxygen. If it's above that, it's going to be more oxygen. So this means that if it's under the stoichiometric ratio, then the nitrogen oxide concentration will be highest. Okay. So then we need to think of way to mitigate this issue. So that's why people come up with this design. So we can reduce the nitrogen monoxide concentration by reduce the peak temperature. We can reduce the temperature to get less nitrogen oxide. We can also reduce the residence time to get less oxygen, right? And we can further reduce the oxygen content in the flame, right? Basically to let it drop onto this side here. So this is basically the idea of how people can reduce the nitrogen oxides. And you can see that indeed this is what people are doing. So this is called the overfire air. Overfire air method to reduce the nitrogen oxides. So what it's doing is basically we have multiple flame nozzles here. So the first nozzle, so the gas mixture will go up this way and then exchange heat with the water, right? So the first nozzle is going to burn at a fuel-rich condition. The fuel-rich condition simply means that there are less oxygen. So if it's less oxygen, then we know that the temperature will reduce, right? The oxygen will also reduce. So this will reduce the pollutants or reduce the nitrogen oxides that's coming from the combustion. So then you may wonder, oh, what happened to the carbon or the hydrocarbon there? Because we know that if there's not enough oxygen, then it's incomplete combustion. So that's why we'll introduce the overfire air here. That's why it's called overfire, right? The air is over the fire. So this way, we can introduce oxygen here, and then further, the oxygen can mix with the unburned hydrocarbons and then further get burned under this fuel-lean condition. The fuel-lean simply means that there are more oxygen. So basically, we're conducting the combustion under low temperature, and then we're also burning most of the fossil fuel in this fuel-rich condition. So in this way, we can both reduce the temperature and also reduce the oxygen amount, and then in this way we can reduce the nitrogen amount. Okay. So in terms of the nitrogen oxide control, people can also use other methods. For example, you can use the catalyst. It's called selective catalyst reduction. There's also selective non-catalyst reduction method. We can also use the adsorption or wet absorption. So there's also a short video on these methods. But right now, the combustion modification, or where it's directly affecting the combustion process, is the most widely used method to reduce the nitrogen oxides that's coming out of the combustion. Okay, so that's all for the contents of this class, and feel free to let me know if you have any questions. Thank you.